our chapter was very active, and it was 6 presidents were from Durki chapter actually. Okay, the chapter was very active from its inception and has organized numerous conferences in the area of geotechnical engineering. Maybe to name a few, the first was the Rock Mechanics in Engineering Practice in 1975. International Symposium on Soil Structure Interaction in 1977, which was attended by many experts from over the world. Then International Symposium on In situ testing of soils and rocks and performances of structures in 1979. Our chapter has organized 4 IGCs from till now. This is 1985, IGC 1985, 2003, 2013, and 2023. Okay. Also, it organized many short-term courses. Maybe at least every year we organized one short-term course. Maybe from any of our departments. We have 3 departments which are working in alignment with the same geotechnical engineering, and we are actually involving in the organization of these workshops. Now, as far as the highest honor is considered, we have honor of delivering IG's annual lectures like Professor Dinesh Mohan in 1980, Professor Shamsher Prakash in 1983, Professor Jagdish Narayan in 1984, Professor R.K. Bhandari in 1986, Professor Gopal Ranjan in 1988, Dr. B.G. Rao in 1992, Professor Swami Saran in 2004, and Professor Viladkar in 2017. So that was you can say it was an aura of our geotechnical engineering chapter here. Okay. So with this brief introduction, I first of all congratulate Ashish to organize this great series, and I am also looking forward to learn from Professor William Coombs on MPM. So thank you, Professor.
Thank you, sir. Now I would like to hand over the session to Mr. Pratik Goel, who is Vice President of Indian Geotechnical Society Student Chapter, and now and on he will be taking care of the session. Pratik, up to you.
Thank you, Ashish. I welcome Professor Coombs for this lecture. Everyone know Professor Coombs. He works extensively in the field of MPM. But before we start the lecture, I request Professor Akansha Tyagi to formally introduce our speaker.
Thanks, Pratik. Dr. Will Coombs is a professor in computational mechanics in the Department of Engineering at Durham University since 2021. And Professor Will achieved Chartered Engineer status with the Institution of Civil Engineers in 2025. Professor Will has secured research funding exceeding £20 million and published over 60 peer-reviewed journal papers in areas such as stress-strain behavior of soils, advanced numerical methods, and fractured mechanics. Recently, Professor Will's research has focused on applications in offshore geotechnical engineering related to offshore wind energy, such as foundation solutions and issues related to cable installation. The adopted computational tool for these investigations is the material point method that is ideally suited to model problems involving large deformations and material failure. And Professor Will is committed to make his research as accessible as possible, including publishing research course in a way that is accessible to early career researchers. And we are very grateful today to Professor Will Coombs to accept our request and deliver lecture on such an important and interesting topic. Thank you. All over to Professor Coombs now.
Okay, thank you, ma'am. Yeah, Professor Coombs, I request you to start the lecture.
Okay, hopefully you can see my slides. Are they visible?
Yes, sir.
Okay, excellent. So thank you very much, first of all, for the invitation to deliver a lecture as part of this series and for the very warm welcome and kind introduction. Really what I want to try and do today is provide a bit of an overview of the material point method and how it works, address some of the issues with the method and how these can be overcome before showing a few of the sorts of results that you can generate using the particular method. Before I get into the details of the presentation, for those of you that are not aware, Durham University is located in the northeast of England, much closer to Scotland and Edinburgh than it is to London. It's a beautiful historic city and one of the locations that's been used to film elements of the Harry Potter films, if you've seen any of those. But anyway, on to the actual topic of today's lecture. So the title is on large deformation soil structure interaction using the material point method. And I first became interested in the material point method a little over 10 years ago now. And that was prompted by my involvement in a particular research project that was looking at how you install cables offshore in order to connect particularly offshore wind farms back to the UK's national grid. For those of you that are not aware, offshore cables need to be buried below the seabed to protect them from accidental interactions with fishing gear or shipping anchors. And one technique for doing this is seabed ploughing, which involves dragging a large plough along the seabed to cut a trench and then install a cable behind it. And that's really what started our interest in the material point method. And since then, we've looked at applying this method to lots of different problems. Problems in biomechanics, problems in collapse of glaciers, and much more fundamentals of the method. We've also continued to apply it to geotechnical problems, looking at, for example, the installation of novel foundation solutions, so helical or screw piles, and most recently looking at drag anchor penetration into the seabed and the risk to buried cables. Now, over these sort of 12 years now, what that's allowed us to do is to be able to model quite interesting and challenging problems that involve a lot of different types of nonlinearity. So the sorts of things we now regularly simulate look like this. So dragging of a shipping anchor into the seabed and modeling the full soil structure interaction process, large deformations, contact and friction, plasticity, etc. But that's required us to really get into the fundamental details of the method and resolve a number of issues that were present in the method when we started looking at it. Initially, we thought we would be able to quite quickly pick up the method and just run simulations like this, and that turned out not to quite be the case. And what I want to do today is mainly spend time talking about the fundamentals of the method and how you can resolve those difficulties rather than just showing lots of interesting and pretty videos of the results. Oh, apologies, we skip back to the beginning. Hopefully, there we are. Okay, so a little bit of an overview of the presentation. What I'll do first of all is just introduce the material point method. I'll then cover two particular issues that I think are really important to understand and to be able to overcome if you want to run realistic large simulations using the method. I'll talk a little bit about how we deal with soil structure interaction in the method, and then just show some numerical examples and conclude with a few observations on where things are. Now, a lot of the basic developments that we've done in the method have been performed in a piece of open source software called Ample. This is something that I published alongside Professor Ogard about 6 years ago. And this particular code is written in MATLAB, and it was designed to be as easy as possible to use by research students who wanted to start trying out things in the material point method. We're also just about to release a Python version. So for those of you that are more familiar or happy with Python, that will be coming out this year as well. And so if you are interested in getting to grips with the method, this is, in my opinion, a reasonable place to start. So a lot of the things I'm showing you can reproduce in this Ample software environment. Now let's get into the basics of the method. So how does the material point method actually work? Now, I assume that most of you are familiar with the finite element method as the kind of default stress analysis tool that we use in engineering. And the material point method shares a lot of similar aspects to the finite element method. And actually, the equations that we assemble and solve are essentially the same as you would do in a finite element method. But there are a couple of fundamental differences that means that it has its own unique capabilities and challenges as a numerical tool. So here, if we start off, the way that we represent our physical material in the material point method is through a collection of points or material points, and these are shown by the dark gray circles on this particular image. And this is trying to represent a physical body that can deform, and that body, the extent of that body is shown by the gray shaded area, and the boundary is the black line. Now, we also need a background mesh in the material point method, and this mesh is effectively a finite element grid. And it's on this grid that we assemble and we solve our governing equations. That can be, the sorts of equations used for stress analysis, or this could be coupled soil water, or whatever set of equations. It could be thermal. We assemble them in the same way that we would on a finite element problem. So what we would do is we would take the information we have about our material held at these material points, and we would map that information, such as the mass, the stiffness, the stresses, onto the background grid. And we use that information to assemble our governing equations. So we assemble those on the discrete locations in the background grid, like you would do in a finite element problem. And then we solve those governing equations. And that leads to deformation of our nodes on our background grid and deformation of our mesh. And it also leads to deformation of our material that we're representing. Now, what we then do is we take that information that we solved on the grid and we map that back to our material points. We map and update the positions, the stress history, any constitutive variables that we're using depending on the material model that we're using at those points. And then the final step is we reset or we completely replace background grid. And then we just repeat this process. And it's this final step of resetting or replacing the background grid, which is the key thing that distinguishes it from the finite element method. And it's the key thing that allows us to model very, very large deformation problems with this particular numerical method without getting into the issues that occur in the finite element method, such as mesh entanglement, mesh distortion, that would typically require you to remesh in your finite element program and then map information between meshes, such as material history. The really nice thing about the material point method, particularly for geotechnical problems where we typically use relatively complicated constituent models that do have a strong stress history, is that information is naturally maintained at the points as they deform through the mesh. However, there are issues by the fact we allow points to move through the mesh, and that's what I'm going to talk about a lot. So one way to describe the material point method is just the finite element method, where we allow the integration points or the Gauss points to move. That's essentially what we're doing. However, that does introduce a number of issues because there's a reason that we carefully tie in the finite element method integration points or Gauss points back to their parent elements. So I'm going to talk about two issues. Now, the most widely known issue in the material point method is something called the cell crossing instability. And this is what we would maybe call in the UK the elephant in the room for material point methods. And it's something you have to resolve if you're going to have any chance of doing reasonable simulations in the material point method. But the other issue I want to talk about, which is less widely talked about, is this issue of small cuts, a small cut instability that is really severe in the material point method, which again, we must deal with. Otherwise, we're not going to have robust and accurate simulations, and particularly not robust simulations. So let's start with the cell crossing instability. And as I say, this is probably the issue, the most widely known issue in the material point method. So what I'm going to do is I'm going to take a step back and think about a very, very simple problem, which is a one-dimensional problem, which is shown at the bottom here. We have a collection of material points representing a one-dimensional bar, for example. Those are the red dots. We have a background grid. Here it's just a grid of line elements, and the nodes of that background grid are shown by the white circles. And what we're going to do is we're just going to apply a force to the end of that bar. Now we'll just use linear finite elements, so we can plot the shape functions or the basis functions of those elements, and you're perhaps familiar with these hat functions for linear finite elements. And as I said, we're going to apply a force at the end of this bar. Now also, when we're solving finite element type problems, we also need the derivatives of these basis functions as well, and those are shown above. Now because we have linear basis functions, their derivatives are going to just be piecewise constant over each of the element. So we apply some load at the end of this bar, and what we're going to do is considering what's going on at this grid node here shown by this grey circle. And so we're only really interested in the shape functions associated with that final node. So they'll go to 1 at that node and 0 at the other nodes, and the derivatives of those basis functions as well. Now, in order to find equilibrium, what we do in finite element methods is we have to have balance between the internal forces generated by the stress in our material with the externally applied loads. And the way that we do that is we map information from the stress in our material to our grid node locations using the derivatives of the basis function and the volume associated with the particular point. Okay, so same thing as in finite elements. In finite elements, we have a Jacobian and weighting information typically associated with our Gauss points, but that's just representing the physical volume associated with that particular point. So this has got to be balanced with the external forces. Fine, we reach that balance and we have some deformation, but at some point what happens is that material point will cross between the element it was in originally into a new element. And when that happens, we get a sudden change in sign of our basis function derivatives. So that's this red part in here. This is the spatial derivatives of our basis functions. And what this is going to do is cause a sudden change in sign of this internal force contribution from that material point. And it's this sudden change that causes the cell crossing instability, because now that force is no longer going to be in equilibrium with external loads, and we're going to have oscillations in our material deformation and stresses in order to find a new balance. And this kills accuracy in the standard material point method. So let's consider a really simple problem, probably one of the most basic benchmark problems we would do in the material point method. And this is the elastic compaction of a column under self-weight. So here, this is the problem that's been set up. We've got a column of material. Now here, the material points are shown by these white circles. We've got a background grid. We've got roller conditions on either side of the base. So this thing can only compress in one direction, only compress vertically, and we load it under gravity. Now, this is a very simple problem where we have an analytical solution in terms of the stress based on initial vertical position in the column. And if you run this with the standard material point method compared to the analytical solution, you'll see something like this in terms of the stress response. And you think, well, okay, it's a finite element-based method, so maybe I just need to refine my grid. So you refine your grid, and this is what happens. You have more points, more elements, and you just see more and more noise. And that's because you're getting more and more of these cell crossing instabilities, which is just polluting your solution and completely destroying the validity really of this very, very simple problem. So if we then were to look at the convergence of our method, okay, so now what I'm doing is I'm plotting the error in the stress versus 1 over the size of the elements. What we expect is as we make our elements smaller, if we know like finite elements, we expect to get a better solution, and you just don't see that. You refine your grid, you refine the number of points that you're using, and you basically see no reduction in the error in your solution. And again, it's because it's just being polluted by this cell crossing instability in this very inaccurate solution. Okay. Now, this was recognized a long time ago, and I say is the kind of the major issue with the material point method. But there are lots of different ways this can be mitigated, and I'm just going to talk about the first way that this was really solved, and actually is the method we tend to use because it's in our experience one of the most robust and easy to use approaches to resolve this issue. Now, this cell crossing instability really comes because we have a sudden change. As a material point moves from one element to the other, it's a big change in that contribution to the internal force within our system and creates these large oscillations. So back more than 20 years ago, Bardenhagen and Kober suggested a change where instead of having all the information about a material point at a discrete location, they said that what we're going to do is associate a domain, a certain area with each of these points. And when it comes to things like the basis functions and therefore the derivatives, we're going to average them over that area. We'll do a convolution of the basis functions over that area. So the consequence of this is basically what we do if we then look at a one-dimensional plot of this. So here's our material point. Here's the sort of the area or the length associated with that material point. These are our finite element basis functions, these hat functions. Then what we're going to do is we're going to just integrate over that domain and average the basis functions. And what that does is it changes the basis functions we use from these finite element ones into something that looks like this. So it has a smooth transition between adjacent elements. So what that does then, if we rerun this column problem, a relatively minor change, is it means that, again, if we look at how our error reduces as we refine our problem, is we suddenly now see convergence in our solution, because we've reduced these sudden instabilities in the method and we've smoothed out the solution by allowing a gradual transfer of information between elements rather than just this sudden change. And it's not just the stress solution that improves, which we can see here with the normalized stress error really going down as we refine our mesh, our background mesh and our material points, but also the amount of deformation we're getting is different. So this is this generalized interpolation or this GIMP approach versus the standard material point method. And you can visibly see the stress oscillations in the standard material point method, whereas in the generalized interpolation material point method, these have basically completely disappeared. So that's one of the issues, which I said was solved a long time ago. And this really transformed the accuracy of the method. There are lots of other ways you can deal with this. A very common approach is to use basis functions that have higher order continuity, such as B-splines, instead of standard linear finite element shape functions. And that's also very successful at dealing with that cell crossing instability. And there are other approaches that have been developed over the years. Now, one of the other issues, though, with the method that is not talked about very widely is this issue of small cuts. And that's what I want to talk about next, and what this is and how we can resolve this particular issue. Now, for a long time, when we're using the material point method, what we would find is we would run a simulation and it would run no problems. And then we would make a small change to the material properties or the geometry or the loading of that problem and try and rerun it, and it would fail. It would fail at some point through the simulation. We couldn't really work out why. We would change the properties again and it might run. We might change it again slightly and it wouldn't run. So really, I suppose, unstable behavior and uncertainty when you set off a simulation if it's actually going to complete or not. And that is a nightmare in terms of trying to use this method to solve any practical engineering problems. Particularly as it was very difficult to predict how to avoid this in the first place. It didn't seem to be helped by having a finer background grid. It didn't seem to be helped by having more material points. It almost seemed completely random. And what we then did is we started to look into more details about why were these simulations failing. And here what I'll show in a moment is just a video of a very simple problem. So this is a two-dimensional analysis of an elastoplastic block under gravity. And basically what we see is this block slumping and sort of collapsing. It's a von Mises type material. Associated flow, very simple constitutive model here. And what I'll do on the video is you'll see the material point deformation, and that will be colored according to the shear stresses. And you'll also see vectors of the displacement that's calculated on the background grid at each step through the simulation. And what we see is something a little bit like this. Okay, so it runs, it collapses, but let's run that again. But what you see at certain points, well, quite often through the simulation, are these very, very large values of displacement on your background grid. Now, actually, I have not scaled at all the displacement vectors here. These are the true magnitudes of the displacements that are being predicted on the background grid. So you can see that some of them look entirely reasonable. They're quite small, so maybe they're tricky to see in terms of the way the material is deforming. But others are completely spurious. You would not expect your material to be deforming upwards under this gravitational loading, and others are just huge, like this final one here. It's this massive, huge displacement being predicted on the grid, not at the material points, but on the grid. But bear in mind, we use this grid information to then map back to the points to get our overall solution of our problem. And it's these large displacements, and they typically, if we watch again, occur at the boundary of our problem. If you look where they're starting from, those arrows, that are causing these simulations to fail. Because what can happen is those very large values of displacement can be then mapped to the material points. They can then displace sometimes in a very unusual way, and that can cause the whole simulation to break down and fail. So how do we get around this? Well, first of all, we were trying to really understand the issue in the first place. So we set up, again, a very simple benchmark type problem to understand what was going on. So this is a two-dimensional problem where we have a block of material. We constrain the base of that material by a roller condition, and then we pin one point so that we actually have a valid system to solve. And what we did was just then move that material. So we just move that material through the background grid. We're not actually solving a problem, we're just translating this material. And then we investigated things like, what does the stiffness matrix look like that we're solving? What does the mass matrix look like that we're solving, to try to understand why we're seeing these instabilities close to the boundary of the problem we were solving. So what do we see? So the amount we're displacing is this value A, and just the grid spacing is this value H. That's pretty consistent across all of the diagrams in this presentation. So what do we see? Well, what we looked at is, for the stiffness matrix, we plotted something called the condition number. Now, many of you may be familiar with the idea of conditioning of linear systems, but if you're not, the condition number of a matrix is a measure of the ratio of the largest to smallest eigenvalues of your matrix, or if you like, some measure of the spread of the magnitude of the numbers within that matrix that you're looking at. Now, large numbers are very problematic because you start to run into issues of accuracy when you solve your linear system. So the stiffness matrix is used to solve for displacements of our problem. And if you have a very large condition number, you basically run into problems of accuracy in your solver. So what you see happen in the standard material point method is actually things are pretty well behaved. The condition number is pretty stable as we translate this piece of material through the domain, until we get to this point here where the condition number spikes right up. But this is entirely correct, because at some point, as you keep displacing this body, the constraint offered by this pin is removed, and then you have a free body. So it's right that you then have no valid solution, basically. So standard material point method looks fine. But remember, we don't use the standard material point method because of cell crossing problems. Instead, we use this generalized interpolation material point method, which smooths out our basis functions, allows us to get accurate stress solutions. So what happens if you plot that method? Well, what you see is something like this, shown by the dashed line. So you see severe spikes in your condition number, and this is linked to when you have very small overlaps between your material points and the elements on your background grid. And what this does is it generates very, very small numbers in your linear system and your stiffness matrix attached to certain nodes. So if you can imagine, if we translate the body such that we have a slither overlapping a particular element, this is going to generate some very, very small stiffness matrix entries for that particular element. Now, it's not just the stiffness matrix that we see these issues. We also see this in the mass matrix, and actually you see these issues with the mass matrix both for the standard MPM, if you use the consistent or the lumped. For those of you that are familiar with the material point method, most material point method implementations, at least explicit ones, use a lumped mass matrix, but you still see this issue of these spikes in the condition number of the mass matrix for these systems. Now, the consequence of that, particularly for explicit analysis, is it really impacts on something called the CFL number. Now, the CFL number, again, is widely used across numerical analysis, particularly in explicit methods, and it's basically a measure of how small a time step you need to take through your simulation in order to remain stable. It's not strictly applicable to the methods we use because we tend to solve things using implicit methods, but it still provides you with a guide on how small a step you can take through your analysis. But if you're using an explicit method, you're absolutely limited by this CFL condition. It basically says how big a time step can you take each time you progress your analysis. And what we see in both the standard material point method, the gray dashed line, and the generalized interpolation material point method is these huge downward plunges in this response where you have to have tiny, tiny steps in order to remain stable. So this is a major problem with the method and causes a lot of analyses to fail. Now, we weren't the first to realize this was a problem. I think we were one of the first to resolve this generally for the material point method. This was actually mentioned by Solsky, one of the originators of the material point method, way back in 1995, so 30 years ago. And they proposed an approach called modified update stress last, which works for explicit methods to a degree. There's been various other approaches, doing things like redistribute these very small entries to other parts of the system, which can be done explicit approaches. There's been some ideas of introducing a very soft stiffness to the background grid for implicit methods, but in my experience, this doesn't really work. This has been dealt with quite effectively for B-spline basis function by the work of Yamaguchi in 2021. And they all talk about the same thing, really. So Solsky talked about the fact that you can get very small values of your basis functions, whereas the internal forces are not necessarily small, and this can cause unphysical results. If you look at other papers, more recent ones, they talk about the need to have tiny time steps because of instabilities. And Yamaguchi, again, is talking about this numerical instability due to ill conditioning. And it's this ill conditioning or loss of coercivity, which is the major issue that's really trying to be combated here. So this is just Solsky's statement in a bit more detail. Now, when we really realized that this was the issue through various investigations that we did, we started to look at other numerical methods that also face this issue. And another class of numerical methods that suffer from this small cut instability are a class of methods called unfitted or cut or immersed finite element methods. And actually, they have a range of techniques to deal with exactly this issue in their particular method. And in particular, the work of Berman from more than 15 years ago now talks about exactly the same issues and way that this can be mitigated to restore the conditioning of your linear system of equations that you're solving. And so the particular way to deal with this that we adopted is something called ghost stabilization. As I say, this comes from the immersed finite element community. So again, let's go back to that sort of diagrammatic sketch I had at the beginning of this talk, where I was showing the material that we're trying to analyze, the physical boundary and background grid. Now, in immersed finite element methods, this is also basically how they solve their problems. You have a description of the boundary, you have full finite elements, and then you have cut finite elements, which you need to discretize in a different way. And then you solve your problem and it can evolve and you keep doing it. It's very similar to the material point method in a lot of ways. So what happens in immersed finite elements? How do they resolve this issue? Well, what they do is they identify the elements that are intersected by the boundary, because it's these elements at the boundary that are causing all the problems. These are the ones that are going to have the small cuts, the small contributions to the mass and stiffness. You determine those intersections, and then you introduce a stabilization. Now, this equation looks horrible at the bottom, and it's not nice at all. I can just talk more physically about what's going on. What you do at these intersections on these boundary element edges is you introduce an additional stiffness term that tries to enforce continuity of the gradient of your solution across those faces. And what this does is it restores coercivity back to your linear system, because you couple those poorly conditioned elements, the ones near the boundary, back to well-behaved elements inside your physical body. So we had to look at how do we adapt this to the material point method. Well, the biggest barrier, first of all, is in the material point method, you don't normally have a description of your physical boundary. You just have a collection of points. We don't actually track the boundary normally in the material point analysis. So we need a different way to identify where we should apply the stabilization. So the way that we approach this is that we identified, well, which elements don't have material points in them. We call those the unpopulated elements. And then we said, well, the boundary between these unpopulated elements and the other elements are the elements that we need to stabilize. So we then said, okay, well, we don't need to worry about these unpopulated elements. They don't take part in the analysis. We just stabilize the elements at the edge of this populated region, the area where we have these material points. And then we'll apply the same stabilization technique to the boundary elements, edges, in order to enforce continuity of our solution. So this goes into it in a little bit more detail. What we have to do is over each of these boundary element edges, we have to perform an integration, which we can do using standard Gauss quadrature. It turns out to be a much easier calculation because we're just using linear basis functions, and this generates an additional stiffness matrix, which we add to our linear system. Now it does introduce a penalty parameter, but there's well-documented literature from the cut or immersed finite element community on how we can link this penalty parameter back to the stiffness of the material that we're analyzing, or the stiffness of the material points that are within the elements that we're considering. So what does this do? So if we go back to this 1D test problem and look at reanalyzing this, so this is the result we saw before for the conditioning of the stiffness matrix. If we apply this stabilization, we basically see that we don't have these problems at all with the generalized interpolation material point method. We restore good conditioning across where it's reasonable. If we then also look at the CFL condition, so this thing that limits the smallest or the maximum time step we can take, we see that if we stabilize if we stabilize the analysis, we basically have a near constant CFL number across this full displacement of the material. So let's go back to the problem that motivated this investigation to begin with, so the collapse of this block. If we apply the stabilization and rerun things, we then see something which is much more physical. Now, in this case, I have scaled up, doubled the size of these arrows, but we've completely lost those spurious, unphysical, large displacements we were seeing without the stabilization. So if we just do a comparison of one particular step, we've gone from something where in the same load step, we were seeing something like this without the stabilization to something like this with the stabilization. And this has completely transformed the robustness and stability of all the material point methods that we use. And it means that we can now set off a simulation that might last a couple of weeks for some of these very large deformation simulations that we run, and just know that we can come back in a week or 2 weeks and we'll have our result. We don't have to constantly be checking to see if things have failed. Okay, so a little bit about soil structure interaction, and then we'll go on some examples. This bit's much quicker, the second half, than the first half. Okay, so how do we deal with soil structure interaction in the material point method? Now, one of the nice things about the material point method is it automatically includes no slip, self, and multi-body contact. So we don't have to worry about internal contacts or material coming back together. That's all handled automatically because you're doing your calculations on a common background mesh. However, this does cause other problems. And if we actually want to model the interaction of, for example, soil with a structure, then we need to do this in a different way. You don't have a very accurate representation of your contact surfaces because, as I said before, we typically don't track the outer boundary of our physical body. So you need a different way to be able to track and enforce the contact. Now, the approach that we take is we assume that when we're doing soil structure interaction problems, that the structure is basically a rigid body. And we use the geometry of that rigid body as the contact surface. And it's on this contact surface that we enforce our contact conditions. We choose to use a penalty formulation for the contact conditions, but you could do this with a Lagrange multiplier or augmented Lagrangian or Nietzsche method, whatever particular flavor of contact constraint you want to impose in your simulation. This, if we combine this then with thinking about generalized interpolation material point domains, and so if we've got some structure coming into contact with our material, we have a number of steps to solve this. So we use the corners of our domains associated with our material points to detect contact. If we detect a contact, we then have a penalty spring that basically enforces our contact conditions. This also has a frictional element as well coming in here, so there's friction between the rigid body and the soil. We find equilibrium between the rigid body and the material points. So we assemble force equilibrium between our bodies as well. And then finally, we do an energy consistent update on our material deformation to make sure things remain stable, basically, because you can see here that initially we get some deformation in our domains, but the way that generalized interpolation material point methods are posed, they always have to be rectangles or cuboids, the shapes of the domains. So we do an update that's energy consistent to reinforce this particular shape. So I say I'll just cover some of the basics on that, but I'm happy to answer any questions, or you can check out papers on that if you want more details. So let's look at a couple of examples. I'll start off with a cone penetration test as a very routine site investigation technique that's done particularly offshore. So if we're thinking about along cabling routes or other foundation sites, then a cone penetration test is one of the most common things that's done offshore. So we basically, what happens is you take a conical tipped probe and you push it into the seabed and you measure the end tip resistance and also the frictional resistance on the sleeve as it's pushed in. Now here you've just got the various different parameters that are used in a single simulation. We do this as an axisymmetric two-dimensional analysis because we have 360 degrees rotational symmetry, so we don't need to do a 3D analysis for this particular case. And what does that look like in terms of then analysis? Well, again, material points are shown by the colored circles in terms of their horizontal displacement. And then the arrows again are showing the grid displacements. You can just see the tip of the CPT coming in here. We deliberately extend it beyond the boundary, the center line, which is the edge of the mesh, so that we don't get any strange artifacts at that corner. And the simulation looks something like this. So you can, this is a zoom in on the right-hand side and the full picture on the left-hand side. You can see that we do sometimes get relatively large displacements on the grid, but these are entirely physical based on this tip being pushed into the seabed. So this all runs, this is like 10 minutes on my laptop, very quick simulations really. Now, do they represent reality? Well, if we compare them to experimental results that were conducted in a geotechnical centrifuge at the University of Dundee for two different relative density sands, so we have a loose sand and a very dense sand, the experimental results and the numerical predictions, you can see that we get a reasonably good match, and this is a prediction based on empirical relationships on relative density. But we can also then improve sort of our model slightly by sort of fitting to these results if we then want to analyze a more complicated problem. So what we would normally then do is we would tune our parameters slightly, or actually we just tune our relative density slightly to get a good fit to experimental results. So here we now have 4 different relative density sands. And then we use these material properties to then predict other things where we don't have a known result. So we could then use these, for example, to predict an anchor penetration into the seabed. So here, the next example is then taking those same material properties, but then running analyses looking at different anchor geometries and seeing how they behave in this particular seabed condition. So here is kind of a more typical analysis that we might do. Here we have a Hall anchor and an AC14 anchor. These are two of the most common anchors that are used in the shipping industry. They're very similar in terms of their size and their mass, but what we see because of differences in the geometry is they have very different penetration depths in this loose sand condition. So you see much more penetration from the AC14 anchor versus the Hall anchor. And we're doing this particular analysis because anchors are the most onerous threat to buried subsea infrastructure, such as cables. And so what we need to try to do is understand how deep will different anchors penetrate into the seabed under different ground conditions. So we can repeat this sort of analysis in different ground conditions. So these are results for a Hall anchor, as I say, one of the most common anchors that's used in the shipping industry. So we've got penetration depth and drag distance normalized by the length of the fluke, the pointy part of the anchor. And here are our sort of validations against geotechnical testing at the University of Dundee and their centrifuge for different relative density sands from very loose to very dense. As I say, we can do this for different anchors. So these will be the same ground conditions, but for the AC14 anchor. And although I'm not particularly going into details of this in the presentation, it wasn't really the focus of the presentation, I think to highlight is industry guidance suggests that all of these anchors should have the same amount of penetration based on their fluke length, and it should be this amount of penetration here shown by this red line. And so what we're doing in this research is really providing much more detailed guidance of how deep different types of anchors will go in different seabed conditions, such that we get more robust advice for industry on how deep we need to bury cables in order to protect them in different ground conditions. And one of the things to highlight here is just changing this anchor type, the shape, we can see a 30% increase in the amount of penetration we see. And the only reason this is possible is because we've developed this robust simulation framework in order to be able to test out these different geometries and directly compare against things that are validated and robust, and we're confident in the results. Okay, so I'll finish things there. Just to close on a few observations. So it's been more than 30 years since the material point method was first developed. We still often describe it as a new method, but at some point we have to decide to stop calling it new. Maybe 30 years is enough. A lot of people describe the material point method as a meshless method, and I think that's not helpful personally. I think it's much better to describe it as an unfitted mesh-based method, because it actually has a lot of the same characteristics and issues that immersed finite element methods or cut finite elements have. And it can be really helpful to look at that literature when you're understanding what you're seeing in a material point analysis and maybe why you're having issues. We've got to deal with the instabilities in this method, particularly as geotechnical engineers, because we do like to use constituent models that have a strong history dependence. But if you don't get rid of the instabilities, these instabilities in the stress history can lead to completely spurious material behavior. If you suddenly have spikes in your strain history or stress history in your constituent model, you can just erase history of your material and get spurious results back, basically. Now, there are still lots of challenges. I've shown some things that have been fixed. 3D large deformation coupled, so soil water simulations are still really difficult and challenging, particularly in terms of simulation runtimes. But there are scientific issues as well related to IMP-SUP, the fact it's a very stiff system, and say this leads to very long runtimes. And boundaries in the method still need more work. Thankfully, over the last few years, there's been more and more work done about boundaries in the material point method, but this is still an area where there's lots to be done. Now, all of the analyses I've shown here are implicit MPM analyses, and you'll see in the literature that the vast majority of people use explicit material point methods. We believe that implicit, it is difficult, it is more difficult than explicit, but it's worth the hassle in a lot of cases, and you can see orders of magnitude improvements in terms of efficiency of simulations versus explicit approach. It also, particularly as we often solve quasi-static problems in geotechnics, it kind of more naturally aligns to the types of problems we're solving. And just as a sort of a final video, this is just another sort of problem that we look at. This is a seabed plow for cable installation, showing how the stabilized faces evolve as the plow moves through the soil. So thank you for the opportunity. Obviously, I gave the talk, but really this is the hard work of a lot of different people over the years, from Tim Charlton, who was my first PhD student on the material point method, to Yun Bing, who worked on boundaries, Michael Cortis, who looked at seabed plowing, Joseph, who looked at B-spline methods and other things. Lei Wang was looking at the screw piles. Giuliano Preti, who's now at Toronto, has done a lot of our coupled soil water analysis work. Nathan Gavin was using this to look at the heart. Ted was looking at higher order continuum theories, so Kozara theories for discrete shear bands. Bradley did some early work on implicit and explicit techniques. Robert's really the person that's implemented our current code, and Sam, who's working on glacier simulations using the MPM. So a big team here. I'll leave up this final slide. Here are some references if you're interested, but you can also always reach out to me if there's any elements of the presentation you're interested in. I saw one question come up about sharing the slides. I'm happy to share the slides from this presentation. All of this work has been published in some way, so I'm happy for that to go out there. So yeah, I'll finish things there. Thank you very much for the opportunity, and I hope you found the talk interesting.
Thank you, sir. That was a very informative lecture. I think we can take up some of the questions. There are plenty of questions in the chat box. So I'm starting with the first question. Actually, the question is about GIMP and CPDI methods. So I think you have explained GIMP, and so can we have a brief description of CPDI method also? Like
Yeah, sure, no problem. So CPDI methods are very similar in a lot of ways to GIMP. There are some key differences between them, though. So the nice thing about GIMP is that you can determine the basis functions analytically for regular grids, which makes them very efficient to implement, actually. So that is an advantage. The way that CPDI methods work is rather than doing a true convolution over your domain, you sample the basis functions at the corners of the domain, and then you average them, and that's what you use for your basis functions. Now, this works fine for a lot of problems, but you do get issues with distortions of those domains unless you do something to reset them. And this is particularly the case for CPDI2, where you have quadrilaterals that are basically like a second mesh. And that method basically fails if you try and do anything which is large deformation soil structure interaction. So they do have some advantages in some particular cases. So if you're doing really big stretching problems, there's some advantages there because you can keep more continuity. But again, it's still, if you stretch them too far, they still fail as well. So they were really popular for a while. They seem to have fallen out of popularity more recently because of some of the issues I've mentioned. People have tended to either stick with GIMP or they've gone to B-splines instead.
Okay, I think that must have answered the question. Now, the second question is, if we create a perfectly smooth interface, it is very difficult to get convergence in FEM. So how much better is MPM in this aspect?
Sorry, what was the other method in
FEM? Like,
FEM?
yeah.
Yeah, well, if you have a completely smooth interface, you're unless you're fully prescribing the motion of the rigid body, then yes, this can be very difficult, and that's because you don't have anything restraining the motion of that body, and also you potentially don't have anything restraining the tangential motion of material points connected to that body. So we haven't really looked at that because you don't have perfectly smooth interfaces in reality. You know, there's no such thing. So, you know, one way, a numerical trick you could do is just have a very, very low coefficient of friction, because it only needs a small amount of restraint to stabilize the simulation. But I would argue that it's to be honest, it's a bit of a spurious academic study if you assume that there's no friction between your interface. It doesn't occur in reality. But as I say, you could just have a very, very small coefficient of friction, which would probably be enough to stabilize your analysis.
Okay. Then the other question is, small cut cells and cell crossing are two major issues in MPM. Where were these corrections method applied to address issues? Were these problems encountered in all MPM applications or in specific cases?
Okay, so I think cell crossing instability applies to MPM in any case where you have moderate deformations. So I think that basically is all cases. And small cuts, it's almost like rolling a dice if you'll get it or not, because it depends on exactly how your material points land relative to your background grid. So you can run a simulation, as I was saying, it runs totally fine. You don't have the issue. It's still there, but it doesn't cause your simulation to fail. And then you can run another simulation where where it fails, and they're almost identical. So it's almost luck if your analysis runs or not, basically. If you're doing explicit, modified update stress last does a pretty good job of mitigating most of this, actually. Implicit, yeah, I think people do some tweaks to get things to be stable or only present the results that work. Because in my experience, it affects almost every analysis you run, or it has the potential to.
Okay. Then does MPM completely eliminate distortion related issues, or does it mainly avoid mesh distortion while still having challenges associated with material deformation and numerical instabilities?
Yeah, that's a really good question, actually. So, so the material point method absolutely does not fully eliminate distortion issues, physical distortion issues in analyses. You see this particularly when shear bands develop, actually, in the material point method. You can see problems occurring where you get concentrated shearing with kind of material points becoming more sparse in their distribution. So you've got almost like dilation in that shear band. And this can actually cause problems if that happens too much, and things can break down. So it removes a lot of the grid-based, the finite element grid-based distortion issues, but there are still other distortion issues that are still present. And actually that's an area which is still, I think, ongoing research in terms of, because one way that you can improve this is by splitting material points. So if you start to get a lot of distortion, you basically split those material points into multiple points, and that can help. But effective criteria for when to do that and how to do that, I think there's still quite a lot of work to be done on that topic, actually. It's a really good question on that, actually.
Okay, so the next question is, what are the advantages of MPM as compared to DEM?
Runtime, mainly. Okay, so yeah, well, this is a really interesting question again, and it depends what you want to do. So some people's there's sometimes a bit of confusion with material point method, thinking it's a particle-based method. It's not. It's a continuum-based continuum-based method, which is much closer to finite elements than it is to discrete elements simulations. Okay. Now, in my experience, discrete element simulations are excellent at understanding particle-to-particle interactions, understanding particulate material behavior at a small scale, developing better constitutive algorithms, etc. But we can't deploy them on realistic scale engineering infrastructure. We just don't have the compute to do this. And simulations can take a very long time with DEM. I mean, they can take a very long time with NPM as well, but they can take a very, very long time. Even just sample preparation with DEM can be very expensive, often the most expensive stage. So I just think they're different tools for solving different problems, but I can't ever really see it. Well, maybe I shouldn't say this. I can't see it in my career of DEM being applied with realistic particle sizes to real engineering problems. I think it's a great tool to understand soil behavior, but not for large scale analysis. It's just my opinion. So I just think they're different tools, basically.
Okay. Sir, one question, are we implementing seismic studies in MPM?
I haven't, but people have. Nothing that stops you doing it. I question why. So what sort of problems you're interested in? Because if you can do your analysis in finite elements, just do it in finite elements. It's easier.
Like liquefaction simulation studies.
Liquefaction,
yeah.
tailings dam failures, large landslides. Yeah, absolutely, you can do it. And people are doing that. It's not something I've looked at myself. In that case, you probably would want to go down the explicit dynamic route rather than implicit quasi-static or implicit dynamic route. But yeah, people are absolutely doing this. So it can be done in the method just like it can be done in finite elements.
Okay, I think we can take one last question. As embedded beam elements are not available in ANORA 3D, what is the best way to model soil nails? Is it better to use separate solid bodies with contact? And if so, how can we realistically represent the soil nail interface properties like friction and adhesion without causing contact instabilities?
Wow, very specific question. Yeah, I don't know the details of ANORA 3D. I thought it was still restricted to 2D, but okay. I mean, if it was me, I would just implement them as embedded beam elements because it's very straightforward to do that in the material point method, just like it is in the finite element method. Yeah, I think that's probably a more detailed question. So if the person that posed that one, you're very welcome to follow up with me on that, so I can understand a little bit more about the problem you're trying to model. Maybe offer a bit more advice, but yeah, I think embedded beam elements as well as can go. So, but if that's not possible in the particular software, yeah, not sure, I suppose, at this stage.
Okay, so I think these are all the questions which were majorly asked. And I request everyone, if you have further any query, you can directly contact Professor Coombs. You can get his contact details on his website at Durham University. So I think with this, we come to the end of today's lecture, and it was a very nice lecture. If any of you want to add anything, I request Professor Akansha Tyagi to say a few words.
Okay, so it was an excellent lecture, and so much to learn. And I really appreciate the efforts made by Professor Coombs to make it more understandable to the people who are new to this field. And the questions here were also really put on well. And even I also wanted to know what is the difference between DEM and MPM. So thanks, Purushottam, for asking this question. And thanks, Professor Coombs, for handling the question answer session so well. So it was a really good, lecture followed by interaction session. Congratulations and thank you very much.
Thank you, ma'am. Now I request Sambit Pani to present a vote of thanks.
Good evening, everyone. On behalf of IGS Roorkee chapter, I am Sambit Pani. Extend the sincere gratitude to the Professor William Coombs and on delivering this quite insightful lecture regarding MPM modeling in large deformation modeling. The way he has been connected the dots like like you can say instability issues with MPM and how to handle this and the practical aspects of the MPM is quite insightful, and I hope that it has helped many listeners and audience across the domain. And we're deeply thankful for your time and busy schedule to share